Hello everyone. Today let us discuss about Newton's laws of motion. We have three laws of Newton. We have to discuss them. But before going to the laws of motion, I just want to tell you about a small definition, that small word called as inertia. Inertia. This word inertia is used about a body. If it is in rest or if it is in motion, a body will have an inherent property. It is the inherent property of the body by virtue of which it cannot accelerate by itself. It cannot accelerate by itself means it cannot increase its speed on its own. Somebody has to give its speed, or if it is in rest, it will be in rest. This inertia is like three types. We have one is inertia of rest, second one is inertia of motion, and the third one is inertia of direction. What is this inertia of rest? It is the inability of the body to change by itself its state of rest. It is inability of the body to change by itself its state of rest. Means if it is in rest, it cannot change its state. That's called as inertia of rest. So the second one is inertia of motion. That means it is the inability of the body to change by itself. It is the inability of the body to change by itself its state of uniform motion along a straight line. Means it is its inability to change on its own, if it is going in the uniform motion, to change its motion. And the third inertia is inertia of direction. It is the inability of the body to change by itself its direction of motion. So on the whole, what we can understand about this inertia is a body cannot do anything on its own. If it is in rest, it stays in rest. If it is in a uniform motion, it continues to be in a uniform motion along a straight line. If it is in a particular direction, it cannot change its direction on its own. Then how can it change its direction? How can it change its state of rest? How can it change its motion in a straight line, uniform motion? For that, it needs external force. So this is about inertia, because we need to know before we start our Newton's laws of motion. Now first law, let us take Newton's first law. So Newton's first law of motion, we can define it as, it says that every body continues to be in its state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. What does it mean? A body continues to be in its state of rest. If it is in rest, it continues to be in rest, or of uniform motion in a straight line. That means if it is going in a straight line with a uniform motion, it will continue unless compelled by some external force to act otherwise. That means if it is in motion, it continues to be in motion. If it is in a uniform, if it is in motion, that is uniform motion, it continues to be in uniform motion. And if it is at rest, it continues to be at rest. Or who has to change its position? Some external force has to change. Some external force has to change its position. Or else we can also say with another statement, the state of rest or uniform linear motion both imply zero acceleration. Therefore, this can be simplified as, that means if it is in rest or in uniform motion, both imply zero acceleration. Zero acceleration, that means they cannot produce acceleration on their own unless some external force acts on them, on the body. So the statement goes like this: if the net external force on a body is 0, its acceleration is 0. That means if the next external force on a body is 0, if outside forces are not there on the body, its acceleration is 0. Acceleration can be non-zero only if there is net external force acting on the body. So this is another one which we can say. So that means I just give you an example. Suppose if there is a ball, and if the ball is lying on a floor, it is in the state of rest. It will be in the rest forever. But when the ball will move, if somebody comes and kicks the ball, then it moves. Or somebody comes and throws the ball, then it moves. That means some external force has to move the ball from its state of rest. A chair is there, it is there permanently there only, but if you push the chair, it will be displaced from that position. Or else, if something is going in a uniform motion, for example, take a toy car without a battery. The small children play with that toy car. Suppose a small child pushes a toy car without any battery, then the car tries to keep on moving on a straight line. It goes on moving. Will it continue like that forever? No. After some time it stops. Why it stops? Some external force stops it. What is that external force? We will learn it now. After some topics we will learn. It is the frictional force. The frictional force is working between the wheels of the car and the floor. It stops. Therefore, it will be stopped. So, if the external force is not there, it continues to be in that only. Now, for example, let us take a spaceship. Let us consider a spaceship out in a interstellar space, far from all other objects, and with all its rockets turned off, has no external force acting on it. In simple words, what I can tell you is, a spaceship is there. It is out of gravitational force. We have sent it far away from the surface of the earth. Now there is no gravity working on that, and let us assume all the rockets are also turned off. That means finally it does not have any external force acting on it. In this case, its acceleration according to this first law must be 0. As we told earlier, if external forces are 0, acceleration is also 0. If it is in a uniform motion, it must continue to move with a uniform velocity. Suppose if it is moving with a uniform motion, then it has to continue to move with a uniform velocity. Then, what about the objects on the earth? You can see, if then on the earth gravity is there everywhere. Yes, on the surface of the earth we have gravity everywhere. Let's say this is the surface of the earth. On that, up to certain height, certain altitude, we have gravity. But some objects are at rest. Just now I gave you an example. Let's take a ball it is there on the surface of the earth, it is at rest. If you take a ball, it is on the surface of the earth and it is at rest. For example, why it is at rest? It is because there are no external forces acting on it. It is not because there are no external forces acting on it. We've just now we talked about that. If no external forces acting on that, because we think this ball is on the floor, no external forces are working on that ball, we think like that, but there are so many forces working. Can you say any force which is working? One is the gravitational force which pulls the ball downwards, that is weight of the ball, which is equal to mg. So that is one force working on that. Then another force will be working, a normal reaction upward. We will learn them all soon. So these are all the forces which are working on the ball. So because they are working on the ball, even then if it is at rest, that means it is not because there are no external forces. It is not because there are no external forces acting on it, but because the various external forces cancel out, that is add up to zero net external force. So I just give you one example. You know the play of tug of war. Let's say this is a rope. Here we have some people, let's say 10 people. On the right side we have 10 people. If they are pulling this side, they are also pulling this side. If the rope is not moving any side, that means let us say they have marked it as the center position as O, and if 10 people this side are pulling, 10 people pulling the rope this side, but the rope is not moving any side, that means it does not mean there are no forces on that. There are forces. 20 people are applying their full force. That means a lot of forces are working on the rope, but it is not moving left side or right side. What does it mean? That it is in equilibrium. Equilibrium means the various forces cancel out each other. That means left side force is equal to right side force. Therefore, they add up and then finally net force is zero. Net external force is zero. So what does it mean? Because many objects are on the earth, they are at rest. That is the sentence we are learning now. It does not mean there are no forces. There are forces. It does not mean there are forces. There are many forces acting on that, but these external forces cancel out each other and add up to zero net external force. Net external force. Let us consider a book at rest on a horizontal surface. Let us consider a book on a horizontal surface. It is subjected to two external forces. So let's take, for example, a table. This is a table. So on the surface of a table, let us assume there is a book. This is a book. And the book, what all the forces it will experience? Force due to gravity, which is working downwards, we call it as weight, which is mg. Another force which works upwards, that is normal reaction r. That normal reaction is always perpendicular to the surface. Therefore, but why the book is not moving up or down? Upward force is equal to downward force. That means R is equal to mg. The upward force and downward force, they cancel out each other, so the book is not moving. So we say the force due to the gravity and another force, that is upward force, That's called as the normal reaction, normal force. Therefore, we conclude from the first law that the magnitude of R is equal to that of W, since W is equal to R. W is equal to R. That means R is equal to mg, meaning that the net force on it must be 0. Upward force is equal to downward downward force. There are two forces working on that. In fact, two forces are working, but upward force is equal to downward force. Therefore, net force on it must be 0 according to the first law. That means the normal force R must be equal and opposite to the weight W. The normal force, which is upward, is equal and opposite to the weight, which is W. One is upward, another is downward, equal and opposite. In magnitude they are equal, in direction they are opposite to each other. In that case, we call it as equilibrium, and the book is not moving any side. So this is another example which we can give about Newton's first law. Now let's move on to Newton's second law of motion. Then, before going to discuss the second law, let's define a small word, that is momentum. Momentum. Earlier I have discussed about inertia. Now I am talking about momentum. Momentum is nothing but product of mass and velocity. It is a vector quantity. It is denoted by small letter p, English letter P. So if you take P as the momentum, P is equal to mass into velocity. Mass is a scalar quantity and V is a vector quantity. P is equal to m into V. It is a vector quantity, and you have to write the dimensional formula. Mass is m, velocity is distance per time, that is L t minus 1. That means m1 L1 t minus 1. And you all know the units for mass, that is kg, units for velocity, meter per second. Therefore, SI unit is kg meter per second for this momentum. So momentum has to be defined first. Momentum is equal to product of mass into velocity. You have to know that word, because it's very important in the coming discussion, and in the coming days we will be deriving the one derivation, that is law of conservation of momentum. Then after that we have to note some point. Observations confirm that the product of mass and velocity is basic to the effect of force on motion. So that means, what does it mean? The momentum is product of mass and velocity. Momentum is product of mass and velocity. It is basic to the effect of force on motion. So whenever force is working on that, then we can clearly see the momentum, that is momentum working in the object. So it is basic to the effect of force. Effect of force means when force works on a body, we can definitely see the momentum in the body. Now let us go for our Newton's second law statement. Let's see the statement of second law of Newton. The rate of change of momentum of the body is directly proportional to the applied force, and it takes place in the direction in which the force acts. The rate of change of momentum of a body is directly proportional to the applied force and takes place in the direction in which the force acts. That means rate of change of momentum. anything with respect to time we write dt. dp means change in momentum, dt means change in time. So the change in the momentum with respect to time, change in the momentum with respect to time is directly proportional to the applied force, that is directly proportional to the applied force, and it takes place in the direction in which the force acts. That means if a ball is there, you are pushing the ball in this direction, force is in this direction, so the momentum also in this direction, that is p is also in the same direction in which the force acts, now let's derive the expression, the most important expression, F is equal to ma. Let us derive this one. F is equal to ma. So just now second law says that the rate of change of momentum is directly proportional to the applied force and takes place in the direction in which the force acts. Now F is equal to ma. Let us prove it. Now let m be a constant mass of the body. Why we said constant mass of the body? Mass of the body generally does not change with respect to time unless we are working on that to change the mass. And let it be moving with a velocity v bar in a straight line. So let us consider there is a body. Whose mass is m, and it is moving in the direction in some particular direction with the velocity v. Then the momentum we all know m into v. So let it be equation number 1. Then as per the second law of Newton, rate of change of momentum is dp by dt, where p is momentum. Rate of change of momentum of the body, of the body, rate of change of the momentum of the body is when a constant force is applied on that, let us say it is dp by dt. Suppose on this body, if a constant force F is applied, then the rate of change of momentum of the body, let it be dp by dt. So there is a body of mass m, and then it is moving with a velocity v. Then after that a force is working on that F, then there is a change in the momentum. Let it be dp by dt. So now we have to prove our F is equal to ma, that is force is equal to mass into acceleration. So from Newton's second law, we have seen F is directly proportional to dp by dt. F is directly proportional to dp by dt. Then after proportionality, in our physics always is equal to symbol we keep with a constant k. So F is equal to k into dp by dt, where k is constant of proportionality. If k is equal to 1, suppose let us assume if k is equal to 1, then F is equal to dp by dt. Let it be equation number 3. Substituting 1 in 3, what is 1? This is 1. P is equal to mv. So in place of P, we will substitute mv, then d by dt of mv. That is, mass is constant, which we cannot differentiate. Take it out, dv by dt. Therefore dv by dt is equal to a. We know that. That is, rate of change of velocity with respect to time is equal to acceleration. Therefore F is equal to ma. Simple derivation, yes or no? So let me tell you once again. According to Newton's second law, F is proportional to rate of change of momentum. Then F is equal to some constant into dp by dt. That constant, if k is equal to 1, F is equal to dp by dt. But P means momentum, that is mass into velocity. Therefore F is equal to d by dt of p. P means mv. But p cannot be differentiated, m cannot be differentiated because it is constant. Then d by dt of v. But dv by dt is nothing but acceleration. Therefore, m into a. F is equal to ma. So, our derivation is F is equal to ma. A famous relationship, very famous relationship, which you need it for most of the numericals. Many numericals we use this formula F is equal to ma. So, you can see that F is proportional to dp by dt. F is proportional to dp by dt as per the definition of second law. Then F is equal to k dp by dt. If k is equal to 1, F is equal to dp by dt. D by dt of mv. M is a constant, take out m into dv by dt. dv by dt is rate of change of velocity with respect to time, that is acceleration. F is equal, therefore a, substitute dv by dt as a, therefore F is equal to ma. We have to write it in the vector form. F bar is equal to m into a bar. F bar is equal to m into a bar. F bar is equal to m into a bar. Now, this is our Newton's second law. After that, let's note some points. The value of k depends on the units adopted for the measurement of force. In SI and CGS systems, the unit of force is chosen that k is equal to 1. K is equal to 1 in only for certain systems. For example, in SI system it is 1. In CGS system also it is 1. In CGS system also it is 1. Therefore, we have taken k is equal to 1 here in this previous derivation. So, why we have taken k is equal to 1? Because in SI system and CGS system k is equal to 1. Second point, force is a vector quantity. It has both magnitude and direction. Third point, it produces acceleration in the body. Force produces acceleration in the body. Please note the points. Fourth point, it can deform a body. As you know, take a some balloon or a football, and take a football or a balloon and apply the force, then the body will become like this. The shape of the body changes. That means that is called as deform the body. Shape of the body changes. Force produces acceleration. Force can deform the body, and F is equal to ma is applicable for ordinary velocities of the body. That means if something is going with normal speed, that is normal velocity, then only you can apply it. That means if the object is moving with the speed of light, that is 3 into 10 to the power of 8 meters per second, for such high speeds we cannot apply this formula. Then after that, and still some more points to be noted. SI unit of force is Newton, very important. 1 Newton is equal to 1 kg meter per second square. How it is? F is equal to ma. For mass we measure in kg, and for acceleration meter per second square. Therefore, 1 Newton is equal to kg meter second to the power of minus 2. And the next one is dimensional formula, m1 L1 T minus 2. m1 L1 T minus 2. Then other systems, let us see. In CGS system its unit is dyne. In SI system it is Newton. In CGS system it is dyne. Please remember the points. And in FPS system it is poundal. Then conversions. We have to know these conversions for numericals. In some numericals they give kg weight, gram weight. In such a case you should know, in such cases we should know, that is what are the conversions. 1 Newton is equal to 10 to the power of 5 dynes. 1 kg weight is equal to 9.8 newtons. 1 gram weight is equal to 980 dynes. All these things you have to know, because we have to do so many numericals based on that. For board exams as well as competitive exams, we need to know all these units. And the last point, in every motion, the force F bar is parallel to the acceleration A bar. In every motion, force F bar is parallel to the acceleration A bar. That means acceleration and force are in the same direction. That means if ball is here, if you have applied the force in this direction, acceleration takes place in this direction only. So that is about that Newton's second law. Now let's go for Newton's third law. Newton's third law, so simple, it is so popular in so many people, like so many people in common language, they use this one even for jokes and all. The people use that is, every common man also knows this statement. To every action there is always an equal and opposite reaction. For every action, whatever the action you take, for that equal opposite reaction will also take place. So action and reaction means that is nothing but force. For every force there is an equal in terms of action and reaction. The third law means nothing but force. Third law means nothing but force, that is, action is also a force and reaction is also a force. For example, let us take two bodies like this. One is A, another is B. Let they come and hit with each other. Then A applies a force on B, let it be FAB, and let it be the force on A because of B, and B applies a force on A applies a force on B, and B applies a force on A. Therefore, these two forces are equal and opposite. Now, the force exerted by A on B is equal to the force exerted on A by B. So this is the third law. So which is very important to be noted. Now, there is no cause-effect relation implied in the third law. The force on A by B and the force on B by A act at the same time or same instant. What does it mean? That means if you are applying force on A, because of that B is applying a force on B. No, this is not cause effect. Because somebody is beating you, you are beating them back. It's not like that. They work at the same time, at the same instant. If two balls are hitting each other, the force exerted on one ball by the other ball is same like the second ball on the first ball. So now let's take the two balls, that only two bodies. One is A, another is B. Then the action and reaction forces act on the different bodies. If action is on B, then reaction is on A, or if action is on A, reaction is on B, not on the same body. Consider a pair of bodies A and B. According to the third law, FAB is equal to minus FBA. FAB is equal to minus FBA. So FAB is equal to minus FBA. That means force on A by B is equal to minus of force on B by A. It is an error to add up the two forces and claim that net force is 0. It is an error. That means we should not add the two forces and say their net force is 0, because they are working on different bodies. Note that point. They are working on different bodies. You can add up the forces working on same body. Just now we have seen a book on the table. The body, that is book, is subjected to two forces. One is weight, another is normal reaction. The two forces are working on the same body, so you can add them. But here these two forces are not on the same body. One is force on A because of B, another is force on B because of A. So you cannot add them both and say that the net force is 0. That is a wrong statement. So what we have learned today is Newton's 3 laws. That is, before learning we have talked about inertia. Inertia, 3 types of inertia, that is inertia of rest and inertia of motion, inertia of direction. So inertia of rest, if something is in rest, if it tries to be in rest, for example, you can take now these questions will be also asked. They are asking like reasons for the questions. Nowadays in the question papers we see so many questions related to the reasons, because we have those question paper pattern is also changed these days. We can see what is the reason of that. Suppose if a passenger is sitting in the bus and then bus suddenly starts moving, then what happens? He feels a backward jerk. He is sitting in the bus, suddenly it starts, he feels a backward jerk because the lower part of the passenger moves with the bus, but upper part remains at rest due to inertia of rest. Note that point, it's because of inertia of rest. So another example I'll give you. Suppose a passenger is standing in the bus and he gets a backward jerk, like he gets thrown backward with a jerk. He's thrown backward with a jerk when the bus suddenly starts moving. Uh, when it suddenly starts moving, this is because if he is standing here now, because earlier example I said the passenger sitting in the bus, now he is standing. This is because the feet of the passenger moves with the bus, but the remaining body of the passenger remains at rest due to inertia of rest, because of the inertia of rest. So he falls backward. So a passenger standing in the bus, he gets thrown backward with a jerk when suddenly the bus starts moving. This the reason is feet is touching the floor of the bus. Then it moves, the feet move with the bus, but the upper part of the body still remains at rest due to inertia of rest. So he gets a backward jerk and he falls down. Then after that these are all the examples of inertia of rest. And then suppose if a passenger is sitting in the bus and then suddenly bus stops, driver gives a brake, then what happens? Suddenly the passenger, he feels a forward jerk now. Why? The body is moving with the bus only. The lower part of the passenger comes to rest with the bus, but upper part moves forward due to inertia of motion. So what is happening here? Passenger is in the bus. Now I am giving you a different example for inertia of motion. First two examples, passenger was sitting in the bus, passenger was standing in the bus. When he falls backward, that is inertia of rest. Now I am saying inertia of motion. Suppose bus is moving and the passenger is also moving with the bus, and suddenly driver gives a brake, he feels a forward jerk because the lower part of the passenger comes to rest when he gives the brake, but upper part does not come to rest because of this inertia of motion. So he falls front side. So this is that is a forward jerk. Now this is some more examples. Suppose there is a horse rider, the person who is on the horse, he is going, and suddenly the horse comes to rest, horse stops. Then what happens? then the lower part of the rider comes to rest with the horse, but upper part of the rider, it moves forward due to inertia of motion. Another example, like I will give you for inertia of direction. Suppose a bus takes a round curve suddenly. We all experience it when a car or bus suddenly takes a curve and we are all thrown outwards. This is because the person tries to maintain his direction of motion due to inertia of direction. That means suddenly if it takes a right turn, we fall towards the left side. If it takes a left turn, we fall towards the right side. We all experience that because we know that is nothing but inertia of direction. So these we can give so many examples. It takes quite a long time. You can take many examples about that. Now the rotating wheel of any vehicle throws out mud tangentially due to inertia of direction. So you can see there are mud guards on the wheels of, if you all go by bicycles, if you go by bicycle, on the top of the bicycle you have mud guard like that. Mud guard means which protects the protects us from mud. Then what happens if it is a rainy season, mud is stuck onto the wheel, then when the cycle is started, that is thrown out tangentially, that means along the tangent, because of this inertia of direction. This is also inertia of direction. So these are various examples still I can give you, but it will take quite a long time. We will meet in the another video with new topic. Until then, bye. God bless you all. God bless you all. Thank you for watching this video. We'll meet in another video. Thank you.